Abstract. Common defects such as loose and missing pins on power fittings seriously affect the stable operation of the power system. In order to find and eliminate defects in time, a method for detecting pin defects in overhead lines based on multi-sensor data acquisition by UAV is proposed. UAV multi-sensors are used to collect images of overhead line pins, and grayscale, denoising and enhancement processing are performed on the images. The watershed algorithm is used to segment the image and remove the disturbing background part. Defect detection is realized based on faster RCNN network. Features are extracted through hierarchical residual convolution. Module RPN is used to delineate regions of interest. Fast RCNN network is applied to realize category confirmation, and detection results are output. The experimental results show that under the application of the research method, the AP values of the 5 types of samples are all above 0.9, indicating that the research method has a high defect detection accuracy. As key components such as pins on high-voltage transmission towers have been exposed to wind, rain and sunlight for a long time, safety hazards such as pins falling off are prone to occur, resulting in failure of transmission lines. This kind of accident has brought great economic losses to the power company, and also brought great inconvenience to the residents' living power supply. In order to ensure the safety of the transmission line, it is necessary to conduct timely inspection on this key component on the high-voltage iron tower. At present, the inspection of transmission lines mainly relies on manual operations, which have problems of low efficiency and poor safety, and the inspection results are greatly affected by objective factors such as personnel skills, weather, and environment. Therefore, intelligent high-voltage tower inspection is very necessary. In order to realize the automatic inspection of power transmission network based on vision, researchers have explored in multiple research directions. Helicopters, UAVs, etc., as aerial flight platforms, have the characteristics of high efficiency, accuracy and safety. Using the cameras installed on the flight platforms, a large number of images including key information such as insulators can be obtained. They have thus become an important way of inspecting power transmission equipment in recent years. The State Grid Corporation of China took the lead in putting drones into the inspection of high-voltage lines and collected a large number of pictures. However, after the drones transmit these pictures back to the ground, a large number of professionals are still required to look at them one by one, looking for the defective pins on the high-voltage towers from the pictures. Although this method solves the security problem, it has low efficiency and high missed detection rate, making it difficult to achieve good troubleshooting efficiency. This makes it difficult to detect the potential defects of insulators accurately, which greatly increases the maintenance cost. Therefore, how to use image processing technology to automate the entire process to achieve real intelligent detection has become a research direction in this field. The inspection of overhead line pins is usually divided into 2 steps: the positioning of the inspection object and the defect identification of the inspection object. Images captured by aerial inspection platforms that contain critical components often also include a variety of cluttered backgrounds such as mountains, rivers, grasslands, and farmland. In the actual detection environment, aerial images have different perspective transformations for changes and lighting conditions. Processing these images is complex and can easily lead to false detection results. Therefore, locating the inspected critical components in the image requires overcoming these disadvantages. Aiming at this point, a method for detecting pin defects in overhead lines based on multi-sensor data acquisition by UAV is proposed. The pin image is collected by UAV multi-sensor, and the collected image is pre-processed to enhance the contrast of the image and reduce the detection difficulty. The watershed algorithm is used to segment the pin image of overhead lines to improve the accuracy of image detection, and the faster RCNN network is used to complete the identification of pin defects of overhead lines. In power transmission lines, pins are widely used as fasteners to connect components to stabilize the entire structure. However, due to long-term exposure to the natural environment, bolts are prone to breakage and pins are lost, resulting in hidden dangers such as large-scale transmission line failures. According to the Administrative Regulations on Operation and Maintenance of Overhead Transmission Lines, the lack of pins is a critical defect. Therefore, it is necessary to conduct regular inspections of transmission lines, and timely check and repair line equipment to ensure the safe and stable operation of the power grid. Traditional transmission line inspections mostly use manual methods, which are intensive and long-term. It is difficult to carry out line inspections in some areas with complex or even dangerous terrain. Compared with the traditional manual inspection method, the current general aerial photogrammetry technology reduces the field labor intensity of personnel to a certain extent and shortens the construction period. However, in the later stage, experienced auditors mainly check the large number of inspection pictures brought back by the drone, which consumes a lot of manpower and is prone to false detection and missed detection. In recent years, with the continuous progress of sensors and remote sensing technology, it has become possible to use multi-sensors of unmanned helicopters to obtain multi-source data, which provides new ideas and favorable conditions for solving the above problems. The use of airborne sensor system for power line inspection is a high-tech that has been widely used in recent years. Using this technology, high-resolution imagery and accurate spatial 3D information can be obtained directly in the power line corridor by flight without power failure. Using this method can greatly improve the efficiency of line inspection work, reduce a large number of field operations, and reduce the cost of line inspection. The data obtained by inspection can not only provide reference for the ledger data of transmission lines, but also provide multi-source data support for power grid management and maintenance through professional analysis and processing. As an important means of spatial data acquisition, UAV mid- and low-altitude data acquisition technology has the advantages of long battery life, low flight cost, high data resolution, and flexible scheduling. It can realize real-time data transmission, and can enter high-risk areas for detection. It is a powerful supplement to satellite remote sensing and traditional aerial photogrammetry, and has formed a situation of vigorous development in parallel with satellite remote sensing and ordinary aerial remote sensing. Especially in the case of emergency response to major natural disasters, low-altitude optical image acquisition in cloudy weather, real-time remote sensing in local areas, and distributed daily low-altitude remote sensing monitoring. The UAV aerial remote sensing system has irreplaceable functions of satellite remote sensing and ordinary aerial remote sensing. The application of UAV in power line inspection and the safety status evaluation of power facilities can make full use of its advantages in cost, timeliness and other aspects, and solve various problems existing in the current manual method. The UAV multi-sensor data acquisition system used in this paper can acquire massive high-precision airborne laser scanning point cloud data, high-resolution aerial digital images, thermal infrared images, and ultraviolet images of power line corridors. The data acquisition system is mainly composed of the following parts: laser, visible light detector, infrared thermal imager, ultraviolet camera, receiver, global positioning system, inertial measurement unit composed of positioning and orientation system. The specific implementation of the multi-sensor capture pin image of the UAV is as follows. Firstly, the time signal and pulse per second signal output by GPS are introduced into the time synchronization controller to perform time synchronization on the time synchronization controller. The synchronization controller first gives time to the laser scanner, infrared thermal imager, ultraviolet camera, and visible light camera. After each sensor receives the PPS signal, the second count is reset to 0, so as to obtain the time accurate to us. The synchronization controller is also used to trigger the camera exposure and send the exposure time to the computer for recording. Through the above steps, the time of POS, visible light camera, laser scanner, infrared thermal imager, and ultraviolet camera data is all unified GPS time, so as to achieve the purpose of unified time reference of multiple data sources. After the time reference is unified, the spatial position and attitude data corresponding to each frame of data acquisition time of each sensor can be obtained from the raw data recorded by the POS at high frequency, thus completing the unified spatial reference. The grayscale of the image is a picture in which the value of each pixel on the original color image is set to R equals G equals B. Among them, each value of R, G, and B ranges from 0 to 255, so that only one set of data needs to be stored when the data is stored. Generally, grayscale is divided into the following four methods: component method, maximum value method, average method, and weighted average method. Among them, the component method is to use the respective component luminances of R, G, and B in the RGB image as the grayscale value of the grayscale image, which can be used as needed in practical applications. The formula for the component method is as follows. In aerial images, often due to the influence of dust and small objects on the ground, as well as the camera itself, some irregular patterns such as points and lines are generated. These points and lines are called image noise and cause interference to image processing. Therefore, it is necessary to denoise the image in the pre-processing stage. According to the signal analysis theory, the plane image in the air domain can be transformed into a frequency image in the frequency domain. Among them, the part with higher frequency represents the part of the original image where the grayscale changes rapidly, while the part with lower frequency corresponds to the part where the grayscale changes slowly in the original image. Therefore, the small interference points that change rapidly can be removed through frequency filtering, and the operation of image noise reduction can be realized. The frequency domain and the spatial domain of the image are in one-to-one correspondence, so this operation can also be transformed into convolution filtering of the image matrix. Through the convolution filtering of the image, different weights are applied to different pixels of the image to construct a new image, which can smooth out the noise points and achieve image noise reduction. Theoretically, a Gaussian distribution has all domains of non-negative values, which requires an infinite convolution kernel. In fact, only the part within 3 standard deviations needs to be kept, and the other parts can be deleted directly. The Gaussian function has 5 important properties, which make it have a comprehensive and extensive role in various processing. These properties show that the Gaussian smoothing filter is a low-pass filter. In the spatial or frequency domain, it is a very effective theoretical tool and practical image processing algorithm. The following 4 items are the important properties of the Gaussian function. The Gaussian filter has strong rotational symmetry, and the ideal Gaussian filter has the same appearance no matter what angle it is viewed from. The Gaussian filter has a single value characteristic. That is to say, when each signal is subjected to Gaussian filtering, the corresponding filtering weights are different. The Gaussian function can resist the influence of time-frequency transformation. Gaussian filters can construct filters of any size. This is because the Gaussian function is unbounded on the left and right, and the unbounded case allows the user to extend it. The smoothness of the Gaussian filtered image depends on the standard deviation. Its output is a weighted average of pixels, with pixels closer to the center being weighted more heavily. So smoothing is softer and edges are better preserved compared to averaging filters. The essence of the Gaussian filter as a smoothing filter is a low-pass filter. The steps of Gaussian filtering are as follows. Step 1. Move the center element of the correlation kernel so that it is directly above the input image to be processed. Step 2. The pixel values of the input image are used as weights and multiplied by the correlation kernel. Step 3. Add the results obtained in the above steps as the output. The original image contains 5 types of targets, such as no defect, missing pins, pin prolapse, missing spaces, and pin deformation. They are unevenly distributed in the image, and there is a situation where one image contains multiple targets and multiple targets. In the original data set of this paper, the number of samples with no defects, missing pins, pin prolapse, and missing gaskets is relatively large, while the number of samples with pin deformation is relatively small. Therefore, This paper generates artificial samples according to the number of samples of different types of targets, and finally makes the number of samples of each type equal. The specific number of samples is shown in Table 1. Conclusion: in addition to working outdoors in harsh environments, most power fittings in the power system also need to withstand the external mechanical load tension and the power load inside the power system for a long time. This makes the pins on the fittings prone to defects such as missing or loose, affecting the stable operation of the power grid. To this end, a method for detecting pin defects in overhead lines based on multi-sensor data acquisition by UAV is proposed. The pin image is collected by UAV multi-sensor, and the image is pre-processed. The watershed algorithm is used to segment the background part of the overhead line. Point 9, which proves the effectiveness of the method.